Hi, it's Sam. In this video, we're going to look at creating our own stereo LFO. So there are a few parameters that I want to include. We're going to be able to control the shape of the waveform, the frequency that the waveform moves, the phase, the amount of stereo effect, which is basically the phase between the two left and right channels of the LFO, the depth of the waveform, and the polarity. So this is what we're going to integrate into our code. And so let's start by creating a phasor, because I want to control all of the LFO's shapes with just one phasor so that they're all going to be moving at the same phase, at the same rate. I don't have to worry about resetting the phase when I change the shape. So now that we have this, I'm just going to lay out, let's see, we can easily take this phasor and add the frequency, and that's just going to be in the left inlet of phasor in hertz. And because this is an LFO, usually we'll change this to be, let's say, between 0.01 and let's say 20 hertz. And I'll change the unit style to be in hertz. By default, I'll say it's 1 hertz. And I'll also change the exponent to 3.3 repeating so that we have a little more resolution in the lower frequencies. Okay. And I'll also turn, let's see, I turned initial enable on and set it to 1, so it'll send out that 1 when the patch opens. I'll add this to presentation. And then the right inlet is for the phase, which I also wanted to be able to control. So really, we've already checked off a couple things, the frequency and the phase. And that's just going to be between 0 and 1. So we can just call this phase, and that's going to be a float between 0 and 1. Make sure you change the unit style to a float as well if you want to use a live dial. And then let's also put initial enable on. Doesn't really matter for the phase, but just good for consistency. So in order to have the stereo effect, we're going to have to make 2 copies of the output of this phasor. And we're going to put that into an MC pack. And the size will be 2, because we're just going to have 2 copies of this. And in the right inlet, we're going to take the signal and we're going to offset it by a certain amount that'll be determined by another dial. And then we're going to keep it within the range of, we're going to keep it in the range of -1 to 1, or actually in this case, phasor goes between 0 and 1. So we want to keep it between the range of 0 and 1 by using the modulo object. So when we're not adding anything to this second instance of the phasor, then it's just going to be exactly the same. But we can slightly or completely offset the phase of these 2 copies by just adding a value between 0 and 1 to the addition object here. So let's just add another dial. Actually, let's use the phase dial because it's going to be the same setup. It's going to be between 0 and 1. and I'm going to call this stereo. So the phase will set the starting position of the waveform, regardless of which copy we're looking at. And then the stereo will offset the phase of the two waveforms relative to one another. And this will make maybe more sense when we're done with the waveforms. We can actually look at them in the live scope. But that's the basic idea of how the stereo effect is going to work. So next, now that we have our copies of the phasor, we are going to use the MC objects so that we can have each copy is going to be processed within the two channels of the different copies of the LFO. So if we have like a sine wave, for example, we can use mc.cycle. And since we're going to have two phasor signals, then they'll go to each channel of the sine wave LFO, and we'll get the offset, the stereo offset, if that is indeed applied to the stereo. So let's try to start off with a sine. And like I mentioned, I want to look at adding polarity. So I'm going to make a quick live.text that's going to say bipolar or unipolar. So when it's bipolar, then it's going to go from -1 to 1, and unipolar will be from 0 to 1. Again, add that to presentation, and I'll say initial enable. And we're going to use a MC selector object with 2 inputs. And we're also going to add a ramp time to smooth out the changes when we switch from bipolar to unipolar. And let's add a 1 here, because we want this to go from 1 to 2. So we're going to add the 1, because live.text will send out a 0 or a 1. So with MC selector, when we're at bipolar, then it's going to be using the first signal in the first inlet. And when it's unipolar, it'll use the second inlet, I guess third inlet really, which will be our unipolar waveform. Let's create an mc.cycle object, and this will be our bipolar sine LFO, and this will be driven by the phasor into the right inlet, which is the phase. So this phasor will just drive the phase of the MC cycle, which goes from 0 to 1, and then it will output the sine wave based on that. And to make it unipolar, all we need to do is take this signal multiply it by 0.5, and then add 0.5, and it'll make it unipolar. And then we kind of need to use a nested MC selector so that we can switch between the different waveforms. So we're going to have 6 different waveforms. And let's make a quick menu to switch between them. So we'll just call this waveforms. And we're going to have sine up, which is basically sawtooth, down, which is kind of reversed sawtooth, square, triangle, and sample and hold. And actually I realized that I switched the order of these. I did triangle and then square. So sine, up, down, triangle, square, sample, and hold. That's the order that I wanted to do them in. And then again, we need to add 1 because the index starts at 0 for the live menu. Then we can just plug this into the first inlet of the MC selector. And then the sine wave can go in here. And let me just kind of scooch this all over. Now to be able to see the resulting waveform, we're going to use live.scope. And we can first, I said I wanted to be able to scale it by the depth. So we can do that by just taking an MC multiplication and then scaling the signal using a dial. This will go from 0 to 100, and I'll make it a percentage for the unit style. And I'll call this depth. And I'm going to use the right outlet because it goes between 0 and 1. Add a presentation, and I want it to default to full depth, so I'll turn on initial enabled at 100. And then I forgot, I also want to make this an MC sig because that'll make it a signal which is smoother than using a max message. So there'll be less discontinuities in the waveform when we're changing the depth. And then lastly, we can use MC unpack with 2, because we have 2 signals, to then unpack the left and right channel. And what I'm going to do is for the second scope, I'm going to make the background transparent, so opacity at 0, and I'll make the wave color like 50%. And then I'll just can overlay it directly over so that we can see the stereo effect. So that takes care of the depth. And so now really all we have to do is build the other shapes and keeping their polarity in mind as we build them. So let's just try out and see how our sine wave is looking. I'll just make an easy DAC so that we can turn on the audio easily to check as we go. So let me turn on the audio and make sure everything's been initialized. Let's see. And I can easily just hover my mouse to check the signal, which is really useful. If you don't have this on, it's under, what is it under? Debug and then signal probe. It's a very useful. So it looks like everything's working here. The signal's coming through. But it's not coming out of MC selector, so this must not be the one that didn't get initialized. So let me select sine. Okay, now it's coming through, and then MC sig. Oh, that's also not been initialized. So you need to make sure everything gets initialized, all these values come through. And that's why it's really useful to use the live UI objects like this, because then you can just go into the inspector and turn on initial enable, and it'll send out their values when you open the patch. You can also go into MC selector and just like the gate object and other objects like this, you can set what the initially open inlet is. So I could have done something like 2 and then 1, so that initially the first inlet, which is the middle inlet, would be set to open. So that's another way that you can ensure that things are set up properly. So now we have this nice sine wave. We can try out the depth. which scales it, and make it unipolar. So now it's only going between 0 and 1. And try out the frequency and the phase. It's not very smooth, but it's just changing the phase. And the stereo effect. So I put it at 0.5. You can see now they're fully out of phase with one another. But if I change the phase, there's still going to be the same amount of phase out of... There's still going to be the same amount of phase out of phase with each other, if that makes sense. But their starting point would be different when the LFO starts up. Okay. Now, if you wanted to use something you could that is tempo synced, you could use a phasor with the lock set to 1 and then send it whatever kind of value you want to use. So for example, if you wanted to use note values, do something like 4n for quarter notes, or if you wanted to use tick values, something like this. And then if you wanted to be able to switch between, because when you're using a phasor that's locked to the transport has to be running for there to be a signal. So if I tried to use it right now, nothing would be happening. So I would have to turn on the transport here. And there we go, now it's running. But when I stop the transport, it will also stop. So in that case, you might want to set up a MC selector and use the transport object. And then I think, doesn't it say if it's transport is on or not? Oh yeah, here we go, transport state. So you could use this to select an MC selector, or just, I guess, a regular selector between the transport locked phasor and the not transport locked phasor. So if you wanted to be able to switch between the two, depending on if the transport is on or off, then you can do that. If you're in Max for Live, you can use plug sync to check if the transport is on or off. And if you're in just regular Max, you can use transport object. So that's another option if you want to have a transport locked phasor. Okay, so let's proceed with the other shapes. So far we only have the sine. Let's move on to the sawtooth. This is going to be kind of a little bit of a crazy patch, so I apologize in advance just because we have all of these selectors to fill up here. So we don't have to do anything for the unipolar phasor because we already have the unipolar sawtooth. And then we're going to send this bipolar to this MC selector as well. However, for the bipolar phasor, we're going to need to rescale 0 to 1 to -1 to 1. And for that, we can just simply multiply it by 2 and then subtract 1. So we just need to add a multiplication and then MC subtraction. I don't think it really matters if you write these as floating points or integers, but it's just useful for me to think about these as signals. And that should be it. So now when I switch to, let's see, there we go. So now we have our bipolar and our unipolar. Great. So that one was pretty easy. Next, we want to do the opposite and have a signal that runs down from 1 to 0 instead of from 0 to 1. And for that, we can just simply use the bang minus tilde. With subtract 1. and that'll give us the unipolar signal. And then for the bipolar signal, we just take the unipolar signal and do the same as we did with the other. So now we have the unipolar and the bipolar. Okay. So far, so good. Next, let's look at what is next? Triangle wave. Okay. So for this, we're going to use the mc.triangle, and you set the peak value phase offset, which was going to be 0.5. And this can go right into the middle inlet. So now we have our triangle wave, our bipolar. Now for the unipolar, we'll just need to scale it like usual. So just like for our sine wave, we just multiply it by 0.5 and then add 0.5. And maybe I should have made this more explicit. So right now for the bipolar, we are going from -1 to 1. Then we multiply by 0.5. Now we're going to -0.5 to 0.5. So the range, the total range is what we want. Instead of a range of 2, we have a range of 1. And then we just need to offset the start of the wave by adding 0.5. So now it's going to go from 0 to 1. Even if the math is not complicated, it's just useful to make this explicit. And I'm not very good at math, so it's very useful for me. And next, now that we have the triangle, let's just make sure that the unipolar is working like expected. Okay, cool. Now next we can look at making the square wave. So for the square wave, we're going to take our selector like usual, and honestly I could just kind of pop this over a couple times. And then also take the bipolar +1 and pop it over here. Okay, I'll make it a little bit easier. And we're going to take the phasor and check when it's greater than or equal to 0. But of course, this one goes from 0 to 1. So we can just take the phasor that is bipolar and check if it's greater than or equal to 0. So it'll be greater than or equal to 0 during half of the, or one period to be, I guess, maybe more specific or precise. And then we just plug that into the unipolar, because that's going to give us a 0 to 1. So now we have that 0 to 1 on and off that we're looking for the square. And then we just need to scale that so that it is going from -1 to 1. So like usual with the multiply by 2, subtract 1, and that will give us the correctly scaled square wave. If we wanted a little more resolution to see that, we could give a little bit of a padding here, like going from -1.05 to +1.05, so that we can kind of see the edge of the waves. That way we can actually see the top and bottom. The very last one I wanted to do was sample and hold, and this is kind of the most, not terribly complicated, but it requires kind of the most setup compared to the other ones. So for this, we're going to need a sample, we're going to need a signal to sample, which will be noise. So just make an MC noise. And then we can use MC sample and hold. So in the left inlet is going to be the signal we're sampling. And then I need to give a trigger value. So I'm going to make this 0 for when we're going to get a sample that's going to be held. And then I want to use the phasor to get to trigger the sample and hold at the rate that it's running at. So I'm going to take the signal and I'm actually going to duplicate it. And the reason that I'm not just using the stereo signal is because that would make it sample the noise at different points in the noise, which I don't want. I want to be able to use the same noise sampled values, just offset using the stereo. So if I were to offset the phasors, that means that the phasors are going to trigger the sample and hold at different times. So that means the noise value will be different, which I don't want, because the whole idea is that these are the same exact signals in the stereo value. I have the same exact signals, just off-put by a small amount, or I guess completely out of phase, but there shouldn't be a completely different value altogether that's being chosen from the sample and hold. So I'm just going to duplicate the phasor using MC dupe, and then want 2 copies of it. And then I can use MC delta, which looks at the difference in, well, let's see how it says it. It says the signal of the sample differences. So let's just take a look at this. So let me use an MC unpack. So when the signal wraps around from 1 to 0, we're going from 1 to 0. So it's a decline of 1, which is why we're getting a -1 spike. So we can use that to do a test. If we have a signal that's less than 0, which only happens for this one sample when it wraps around, then we should get a 1 at that time, and that we can use as the trigger for the sample and hold, which is looking for a value that's larger than 0. So that will give us our sample and hold value. And noise is giving us values between -1 and 1. So you can see that we're getting, let me make this a little bit faster, we're getting lots of random values between -1 and 1. So to make it unipolar, we can just simply use the absolute value. That's a quick and easy way to just give us values between 0 and 1. Now the question is the stereo effect. How can we make it so that we have the stereo effect? Because like I said before, if we were to use the phasors offset from each other, that would create a problem where we're getting different values from MC noise, which we don't want. We want the same value, just offset. So what we can do instead is kind of fudge it by delaying the signal. So we're going to use MC delay, and I'm going to make the maximum delay size just 44/100, and I'll just set the initial delay as 0 milliseconds. We're just going to pop that in. Now for the first copy of the sample and hold, we're never going to want to delay it. So we're going to use the apply values message to set what the delay should be. So we're going to apply values to the delay attribute. And for the first, we're going to say 0 because we don't want to change the delay of the first channel, but we do want to change the delay of the second channel. So we're going to change that. But how do we calculate it? Well, the delay in milliseconds should be the stereo offset times 1,000 divided by the frequency, which is the rate. So this will give me the delay in milliseconds, but I believe I need to translate that to samples for use with MC delay. So I'll put that at the end here. And then we just need to do this calculation. So I'll use the expr object to make it a little bit more straightforward. So the first input's going to be a float, which will be the stereo offset amount, times 1,000, and that's going to be divided by a second float. And since the second inlet is cold, I'll have to use a trigger to make sure that it updates the calculation if that second inlet is updated. So this is where I get the rate. So I'll just go over to the rate and plug this in. And then for the left inlet, I just need to get the stereo offset amount. And then that should correctly give us the offset. So if I go to unipolar now, and I give this a little bit of offset, you can see now that we have the same exact values. Make it a little bit slower, maybe it'd be easier to see. I have the same exact values, but now they're being offset in time from one another, which will give us that stereo effect. Okay, so that should cover everything I wanted to look at. Now, if we were to put this in presentation mode, we can set it up so that we can access the different parameters. And of course, we would want to eventually use this to control things in our patches so that when we have something like, say, filter cutoff or something like that, we can just take the signal, and it probably would want to encapsulate all of this, and then we can just use the signal to control different parameters. But hopefully you found this useful. If you have any questions or clarifications, please let me know. If you want to check out, if you have Max 9, there is a built-in LFO, actually a stereo one too. So it's the abl.dsp.stereo LFO. So you can check that out and take a look at its help and reference file. Something you can also use, but it's useful if you want to be able to extend an LFO or just understand how it works. Of course, it's useful to build it yourself like this. So have fun patching. Until next time, class is dismissed.